Hello, welcome to another video for the course Engineering 204 Engineering Design. In this video, we'll continue our discussion on assembly modeling in Creo. In the previous lecture, we started talking about assembly and we assembled a very simple gear train where we took two identical gears and just put them in a manner where they will be able to work as a functioning gear train, but we were not able to implement that functionality. In this lecture, we'll see how we can have movable joints in Creo, and at the end, we'll also see how we can prescribe a gear connection between two gear components so that when you move component one, the functional relationship as prescribed by the mechanics is communicated to the second component, and the second component, the second gear, would respond to that as if it was an actual gear. Very brief introduction to mechanism analysis. This note, which is accompanying this video, will be shared with you. And even though I'm not going through it in detail in this video, I expect you to read through it. It's a very simple, high-level listing of important points about mechanism analysis, degrees of freedom. A mechanism is a mechanical device that transfers motion and or force in a predetermined fashion, and a mechanism is made up of multiple linkages. Over here, there are different examples of some links. Mostly links that we use in a mechanism have two nodes where they're connected to two um, adjacent components, but they can have three or more nodes as well. We've already talked about degrees of freedom. Over here, there is a formal definition of degrees of freedom, and based on the degrees of freedom between two moving links, we can have different kinds of joints. As we'll see very shortly, Creo offers us a whole host of joints to choose from, and different joints have different degrees of freedom. In this document, I talk about some of the more popular joints that you might be encountering. We'll only be talking about three in this particular video, and I'll leave the rest for you as an exercise. The first joint that we'll be talking about is a pin joint. A pin joint is a single degree of freedom, and that degree of freedom is a rotational degree of freedom joint. The example could be the human elbow. So this elbow is pin joint whereby there's only one degree of freedom, and that's rotational degree of freedom about this axis. This is an example of a pin joint. This is your pin about which you can rotate your parts. In this document, I also talk about the major steps that you have to follow to implement these joints in Creo. For a pin joint, first you have to define the axis, this axis about which your components would move, and then you also have to limit the translation about along this axis by fixing planes. We'll see how to implement that in Creo. The second joint that we'll talk about is again a 1 degree of freedom joint, but that single degree of freedom now is a translational degree of freedom, where you can translate your part along one axis, and that kind of a joint is known as a slider or a prismatic joint. Again, a very common joint found in real life applications. The most common example would be the piston cylinder arrangement. You have a piston which reciprocates up and down in a cylinder, and that's 1 degree of freedom. There is no rotation happening in any direction, and it's just translating to and fro, reciprocating along one axis. So this is an example of a piston cylinder arrangement where it would reciprocate about one axis, so 1 translational degree of freedom. The third kind of a joint that we'll look at is a cylindrical joint, which is a combination of a pin joint and a slider joint, in that it has 2 degrees of freedom. The first degree of freedom is a translational degree of freedom, and the second degree of freedom is a rotational degree of freedom. An example of that is this lock, this traditional kundi, in which you not only move your part, let me change the color, not only translate this about its axis, you can also rotate this cylindrical part about the same axis. So it has 2 degrees of freedom, one translational and one rotational. So in some ways, it's more forgiving. It has less constraints than uh, a, a prismatic or a slider joint. Because in a slider joint, you can only reciprocate it. You don't allow it to rotate. So in applications where you don't really care about whether your reciprocating part is rotating or not, it's better to not impose more constraints than you have to. So in that case, it would be advisable to go with a cylindrical joint. Other joints that we won't look into, but they're very easy to implement if you follow the same methods as we'll learn for the first 3 joints. Our ball, also known as a spherical joint. Our shoulder muscle is an example of a spherical joint. It has 3 degrees of freedom, and all 3 are rotational degrees of freedom. Another example is a joystick that you might use on your gaming consoles. So a ball or a spherical joint is a 3 rotational degree of freedom joint. And lastly, planar joints are joints that have 2 translational degree of freedom and 1 rotational degree of freedom. The fact that they have 2 translational degree of freedom means that they allow movement along a 2D plane. So an example of that is a chessboard. So the chess pieces can move anywhere they want, but only in this 2D plane. And that's an example of a plane joint. Bearing joint, I'll leave that up to you to review on your own. And as we'll see that once you start implementing joints in Creo, Creo tells you that there is a movable joint using these symbols. This symbol represents a rotational only degree of freedom. This symbol represents a translational only degree of freedom, and these are symbols for cylindrical and ball joints. We'll mostly be exploring these. So with that, now let's get started on Creo. So I'll open my Creo parametric. Remember that we are using Creo parametric 9.0. So let's wait for it to open up. Okay, so it's finally booted up. I'll set my working directory to the folder where I want things to be saved. And in this particular case, I already have a few part files that I'll be pulling from. And then I'll start a new assembly project, even though the joints are capable of moving, but the fact that it's composed, our project is composed of multiple components means that it's still an assembly file. I'll call it gears. And I have a new assembly project starting. These are components that we have used in the previous video as well. So we have the base plate, which is the back plate. And if you want to confirm that you're selecting the correct part file, you can enable this preview from here. And this is the base plate that we had previously. I've made some additions to it, which were needed to explain the implementation of these joints, and they're very simple additions, so you should be able to implement them on your own. So I'll start with this. So I'll import the base plate, which is the ground connection, the connection which will not be moving in my mechanism, and I'll assemble that as I always assemble the first component of my assembly by using the default constraint. So the default constraint makes our parts principal planes coincident with the principal planes, these 3 planes of the assembly. The part is fully constrained. We'll click OK, and in this way we've imported our ground linkage, which is the first immovable linkage of our mechanism. So what I'll try to implement now is a pin joint. So I'll import a gear the same way I imported it previously. This is the same gear that we've been working on. And instead of fully constraining it, I will give it a pin connection where it can move about one axis, and I'll prescribe that axis. So how you implement different kinds of joints in Creo is by using this, using this drop-down menu where it says connection type and selecting the kind of joint you want. By default, it's user-defined, where we are individually prescribing constraints of the component being added in reference to components already in the assembly, but now we want to prescribe a movable pin joint. So select pin joint from here, and if we go to our notes and look at where we're talking about pin joints, these are the 3 steps that we need to follow. The first thing that we need to define is the axis about which the rotation will take place. So let's implement that. So what I want is that I want my gears axis, which is this axis. You can select it from here. It's not letting me select it. Oh, sorry, the connection type was selected incorrectly. So in pin joint, select the axis of the gear. You can either select the axis from here, or you could just select the bearing surface, the cylindrical surface, and that automatically chooses the axis for you. I want this axis to have a pin connection with this axis over here. Again, you can try to select the axis, you can disable everything and choose only axis from here, or you could just select the cylindrical surface, and that is the first requirement of defining a pin joint. So now you've defined the axis about which your pin joint would be established. Next, you need to prescribe translational constraints, because even though you've told Creo that you want your part to be rotated about that axis of the base plate, your part can still move along that axis. So to stop this translation along the axis of rotation, we'll prescribe the second set of constraints. Your axis alignment done. Next, we'll constrain the translation, and you can do that by selecting any 2 planes, one from the component, one from the assembly, and using those as constraints. So I'll use this plane, and I'll select this plane, and I'll select the kind of constraint to be distance, because I want my gear to be at some distance from this plate. Let's say that I want it to be at 1.5 inches. I think I'm currently working in inches. I'll make note of that, which is not a good practice. You should have been working in mm, because everything you designed was in mm. So don't be lazy like me and work in the same system of units. The next thing that you've done is that you've constrained Creo to disallow motion of your connections along the pin axis. And now if you look at the status, it says connection definition complete. It doesn't say fully constrained, because you're using a movable joint, and a movable joint by definition is meant to allow motion. And if it's fully constrained, then you won't be able to allow motion. And we're happy with this. We click OK, and you see over here, you see a square or a rectangle with a dot inside, and that's the symbol for a movable connection. And you can verify the motion of this joint by, let me just get rid of all the datums, by using the drag component tool. If I try to pull this out, it's not being pulled out because I've limited its translation, but it can rotate about its axis over that pin connection that I defined. So that is how you can define a pin connection. the following is an optional constraint that you can add, you might need to add in some situations. For example, when you are moving this link about its pin connection, you don't want it to move all the way to the back, because that would mean that it's cutting through this material, and Creo doesn't know whether you want it to not cut through that material or not. You need to manually prescribe that this pin motion is permitted between these angles. So that's an optional additional constraint in a pin connection that you can add, which is this third bullet point over here. You can set limits of rotation. I'll use this as an example. Not that we need our gear rotation to be limited, but if you need to define that, you'll go to the step where you were defining your pin connection. The first thing that you defined was the axis of rotation. The second thing that you defined was the translational constraint along that axis. And then the third thing that you can define optionally are constraints to limits to the rotation. And for that, you need to define two planes. Let me enable the planes again, and I'll show you what that means. You need to define a plane on your component and then a plane on your assembly. And then you can use these two as references, that the angle between these two planes is allowed to vary between a lower limit and an upper limit. You have selected those two planes, and it doesn't really matter which references you select, because the limits that we define, the minimum and the maximum limits, you will choose based on your requirements, and they can vary depending on the constraints, depending on the planes that you choose. Let's say that I want my gear to be able to rotate from this point all the way to this point. So I wanted to be able to rotate 180 degrees starting from this orientation. And what I can do is prescribe a minimum limit and a maximum limit. The current position of my gear in degrees is minus 90 degrees. You could either choose this, say that this is minus 90, and this maximum is plus 90, minus 90 plus 180, and prescribe those over here. Right now, the minimum limits are minus 180, maximum limit is 180, which means entire circle 360 degrees, and plus 90. Click OK, and now when you rotate your gear, it will only rotate that 180 degree which is allowed. In this way, you can prescribe constraints. A very useful way of defining those limits is not by using these values from the current position. It's by redefining the 0 position. So let's say that you want your motion to start over here, and the value is minus 71. That's somewhat arbitrary. So if you press this button, which is set 0 position, now this value is considered 0. And you can set your minimum value to be 0, and the maximum value which is allowed, you want it to be 180. You can set the maximum limit to 180. And now when you move your part, it will be allowed to move sweep through those 180 degrees, but you did not need to use a random number like 71. You use that as your 0 value, as your 0 position, and then from that 0 position, you defined the number of degrees you wanted your part to be able to move. So that's how you can define a pin joint. Now let's quickly see how you can define a slider joint. A quick reminder what a slider joint is. A slider joint is a 1 degree of freedom, 1 translational degree of freedom joint, which can translate about one axis. So the things that you need to define in Creo are the following. You define the axis or the edge along which you want your part to translate, and then you may provide additional constraints to stop its rotation. Let's implement this in Creo and see how it works. So what I have over here is I've made this cylinder. It looks like it's incomplete over here, but I've just made it transparent. Let's go with shading with reflections. So I've just made it translucent. This is a cylinder, and I want a piston to reciprocate through the cylinder. So that's an example of a prismatic or a slider joint. So I'll import my piston. I made this piston. I'll confirm that it's the right component that I'm looking for. It is. I'll import this. I'll roughly orient it the way I want to orient it. I want it to be oriented this way. I can move it slightly closer. You don't have to, or everything will happen automatically, but just to make things more manageable. And then I'll define a slider joint from the connection type menu. Slider, Creo calls it a slider joint. Sometimes it's also known as a prismatic joint. And the first thing that you need to define in a slider joint is the axis about which your component would be able to translate that one translational degree of freedom. I'll select this axis over here, and I'll select this rounded surface of my piston to provide the second axis. That's the first constraint. And now my part will be able to move up and down, but it still has one more degree of freedom whereby it can rotate. I don't want it to rotate. I want it to stay axially in the same position. So for that, I'll, similar to how I defined the rotational limits on the pin joint, I'll select a plane on my component. I can select this plane, and I'll select a plane on the assembly. And the angle between these two planes will now be maintained constant. And in this case, they're both parallel. So the distance between these two parallel planes will be maintained constant, and you can't change that distance because that distance is defined by the axis. So the distance between this axis and this plane defines what that constraint is, by how far the central plane of the piston is from this second plane, and these two planes are parallel. So now your part can't move about its axis, and your connection type is fully defined. So now if we move our piston, we try to rotate it, it can't rotate, but it can slide up and down. But if you see, this is a bit unrealistic. You don't want it to be able to reciprocate indefinitely. You want it to be able to reciprocate within the cylinder. So for that, similar to the pin joint, where you can optionally define rotational limits, in a slider joint, you can optionally define translational limits. So I'll go back to my slider connection, and I'll prescribe a third set of constraints, which would be translational limits. The first thing that I defined was the axis about which my part, along which my part will translate. Then I limited its rotation by giving it planes which need to be kept parallel, or if you selected different planes, they might have had to be kept perpendicular or at a certain angle, but what that does is that it stops your part from rotating. And the third thing that you now will prescribe are limits to the translational motion. And what I'll do is that I'll select this plane, I'll select this plane on my part and some plane on my assembly. Doesn't really matter because I'll be defining these limits based on where I want my piston to be. So I'll bring it to that part. And right now, the distance between these two planes is 3.28. So the distance between this plane and this plane, the two planes that I selected is 3.28. But I don't want to work with these awkward values. So I'll make this my zero position. But in fact, I just realized that I don't want my bottommost position to be that. I want it to be this, where my piston top is barely inserted in the cylinder. So the distance between these two planes is now 1.47. I'll use that as my zero position. And then I'll see what is the highest point where I might want my piston to be. I want that to be 2.38 inches, in this case, above the zero position. The minimum limit that I'm defining is 0, and you don't need to define two limits. You can just define one limit. If you want a lower limit and not an upper limit, you can keep the maximum limit at this infinite value or just not check it. And I want my maximum limit to be 2.38. And now when I move my piston up and down, it stops automatically in these limits. Later on, we'll see how we can add servo motors and automatically make these things rotate, but those rotations have to be constrained, and this is how you can constrain those movements. One thing that I want you to notice is that even when I try moving my part side to side, it's not rotating, because it's been told that two planes need to be kept parallel, but it can't translate. Had we not used a slider joint, but instead used a cylindrical joint, then we did not need to prescribe that additional constraint of two planes being kept at a particular angle, because rotary motion in that case would have been allowed. So let's go back to our slider connection. And I'll just quickly do it, but if you can implement it from scratch. If instead of a slider connection, I now use a cylinder connection using the same constraints, and now when I move my part up and down, it still moves within those constraints along the same axis, but you're probably noticing that it can also rotate about its axis. Yeah, so, and that's because a cylindrical joint has a rotational degree of freedom as well. So if you need an application where you don't need this to be constrained, or this motion is already being constrained by another connection type and this is redundant, then it's better not to add more constraints than you need to. So that's everything for this video. What we talked about over here was how you can make movable assemblies in Creo, and in the next video we'll see how we can make two gears mesh and how we can prescribe a gear relationship between two gears. As I mentioned, I'll invite you to look into ball and planar joints on your own, and maybe even a bearing joint type. You'll select those similarly from this menu. Play around with them. If you have any questions, I'm happy to discuss. Thank you for watching this video.